Hey, my friend, tonight, let's take a quiet journey together, not through space, but through time itself. We'll drift gently into the strange, beautiful truth that every moment you live is part of a personal voyage through the universe. So settle in, get comfortable, and let the ticking of the seconds become a soft background hum as we begin. Chapter 1. What is time, really? Time is one of those concepts that feels so familiar we rarely stop to question it. We sense it passing in the rhythm of our days, in the slow brightening of morning, in the ticking of a clock on the wall. We feel it when we wait for something to happen, and we measure it when we try to be precise. Yet for all its apparent simplicity, time is one of the most elusive and puzzling aspects of reality. The more closely science has looked at it, the less it has behaved like the simple, universal background we once thought it to be. For much of human history, time was assumed to be absolute, a steady river flowing at the same pace for all people, in all places. The ancient Egyptians used sundials, tracking the shadow of a gnomon to mark the hours. The Babylonians divided the day into segments of 60, a system that still lingers in our minutes and seconds. Mechanical clocks emerged in the Middle Ages, ticking away in city squares, giving the impression that time could be perfectly uniform. In Newton's physics, this was more than just an impression. It was a foundation. Isaac Newton imagined time as an unchanging, universal backdrop, flowing evenly and independently of anything else in the universe. According to this view, the time between two events was the same for everyone, everywhere. But our understanding of time changed radically in the early 20th century. Experiments and theory began to suggest that time is not the universal constant we once assumed. Instead, it is woven into the very fabric of the universe, and it can stretch, compress, and even behave differently depending on where you are and how you move. This shift in thinking began with the work of Albert Einstein, who showed that space and time are inseparable parts of a single four-dimensional continuum known as space-time. Einstein's breakthrough was not just in describing how space and time fit together, but in revealing that they are not fixed. They are dynamic, flexible, and influenced by the presence of matter and energy. The speed at which time passes depends on factors like motion and gravity, meaning two observers can disagree on the amount of time that has elapsed between the same pair of events. This is not an illusion or a trick of perception. It is a real, measurable effect that has been confirmed by countless experiments. To grasp why this is so surprising, it helps to think about what we actually mean by time. In science, time is not simply the ticking of a clock, but a measure of change. It is the ordering of events, what happened first, what came after, and by how much. In classical physics, time was treated as a stage upon which events play out. But in modern physics, the stage itself can bend, twist, and change shape depending on what is happening within it. This is why time is so deeply connected to motion. One of Einstein's key insights in special relativity is that the speed of light is the same for all observers, regardless of how they are moving. This may sound like a small technical detail, but it has extraordinary consequences. If the speed of light is fixed, then space and time must adjust themselves to preserve that constancy. And they do so by allowing time to flow at different rates for different observers. Imagine two people, one sitting still on Earth and another moving at a significant fraction of the speed of light. For the person in motion, time will pass more slowly relative to the person at rest. This is not a matter of perception, it is a physical difference. If they carry identical clocks, each will find that the other's clock ticks more slowly. This phenomenon, known as time dilation, is not a matter of faulty instruments. It is built into the structure of space-time itself. This strange behavior is not confined to theoretical thought experiments. It has been observed and measured in real life. Particles called muons, created when cosmic rays strike Earth's atmosphere, live for only a fraction of a second before decaying. If they were at rest, they would never survive the trip to the surface. But because they travel at nearly the speed of light, their internal clocks run slower relative to Earth's frame of reference, and they last long enough to reach detectors at ground level. In laboratories, scientists have placed extremely precise atomic clocks on fast-moving aircraft and satellites and compared them with identical clocks on the ground. The results match Einstein's predictions perfectly. The moving clocks register slightly less time having passed. Gravity, too, plays a role in shaping time. General relativity, Einstein's extension of special relativity, describes how massive objects warp space-time around them. This curvature affects the passage of time itself. In a stronger gravitational field, closer to a massive object, time runs more slowly compared to regions with weaker gravity. Experiments have confirmed this as well. Two identical atomic clocks, one placed at the base of a mountain and another at the summit, will tick at slightly different rates, with the clock in the stronger gravity at the base running more slowly. This effect is tiny in everyday life, but becomes extreme near black holes, where time can appear to nearly freeze for an outside observer watching something fall toward the event horizon. All of this means that time is not a universal metronome ticking away at the same rate for everyone. Instead, it is local. Each observer carries their own clock, and while those clocks may agree under some conditions, they can also diverge in measurable ways, depending on motion and gravity. The common idea of a now shared by the entire universe is an illusion. In relativity, simultaneity is not absolute. Two events that happen at the same time for one observer may happen at different times for another. Still, for most of us moving slowly through relatively weak gravitational fields, these differences are so small they escape notice. A person walking down the street experiences time almost identically to someone standing still on the corner. But zoom out to cosmic scales or speed up to relativistic velocities, and these subtle differences grow into something profound. Astronauts aboard the International Space Station orbiting Earth at about 7.7 kilometers per second experience time slightly differently from people on the ground. Over 6 months, the difference might be only a fraction of a second, but it is real and measurable. Understanding that time is relative challenges deeply ingrained intuitions. Our brains evolved in a world where such effects are too small to notice. We are accustomed to thinking of time as a single thread that everyone follows together. Modern physics shows us instead that time is a tapestry of many threads, each belonging to its own observer, all woven together by the geometry of space-time. And yet, even as science reshapes our understanding of time, it does not take away its mystery. We can describe in exquisite detail how time behaves under different conditions, how it stretches and compresses, how it connects to motion and gravity. But the question of what time truly is, why it exists at all, why there is a past and a future, remains unanswered. We can measure time, manipulate it, and account for its distortions, but we cannot yet say why it flows in the first place, or whether it flows at all in the way we imagine. It is here that physics brushes against philosophy. Perhaps time is not something that flows, but rather a landscape through which we move. Perhaps past, present, and future all coexist, and our consciousness merely experiences them in sequence. Or perhaps the flow of time is an emergent property of deeper laws we have not yet discovered. In this way, time remains both the most familiar and the most mysterious aspect of reality, a constant companion in our lives, yet a puzzle that resists complete understanding. As you sit here now, you are moving inexorably forward in time, even if you feel still. Every beat of your heart marks another step into the future. And somewhere, far away in the universe, there are places where that step is slower and others where it is faster. But it is always yours, a personal journey through a dimension we all share, yet never experience in quite the same way. Chapter 2. Einstein's breakthrough, Time is Relative. At the dawn of the 20th century, physics stood on what seemed to be a solid foundation. Newton's laws had reigned for more than 2 centuries, predicting the motion of planets, the fall of apples, and the swing of pendulums with unfailing accuracy. Space was seen as an immutable stage, time as the ever-flowing river upon which events unfolded. Together, they formed the backdrop to all physical phenomena, absolute and unaffected by anything happening within them. But there were cracks in the foundation, small at first, yet persistent enough to trouble the most attentive minds. These cracks appeared in the study of light and electromagnetism, and they eventually forced physicists to question ideas that had seemed self-evident for generations. For centuries, people assumed that motion through space could always be measured relative to some ultimate rest frame, a cosmic zero point against which all motion could be judged. When it came to sound, that reference frame was the air. When it came to light, physicists assumed something similar existed, an invisible medium called the luminiferous ether. Light, it was thought, traveled through this ether in the same way that waves travel through water or vibrations through air. This made perfect sense at the time. If light was a wave, then surely it needed something to wave through. And if such an ether existed, then moving relative to it should subtly change the speed of light you measure. In 1887, Albert Michelson and Edward Morley set out to detect this effect with an exquisitely sensitive experiment. They expected to find that light moved slightly faster in one direction than another, depending on how Earth was moving through the ether. But they found nothing. The speed of light was exactly the same in all directions, no matter how they measured it. The ether, it seemed, was undetectable. This was deeply puzzling. It contradicted the intuition that speeds should add and subtract in a straightforward way. If you are running toward a sound source, the waves should reach you faster. If you are running away, they should reach you slower. Why should light be any different? Some physicists tried to save the ether by inventing ad hoc explanations, such as the idea that objects moving through it might physically contract in the direction of motion. Others suspected something more radical might be at play, but they lacked a coherent framework to explain it. It was into this climate of uncertainty that a young Albert Einstein stepped in 1905, in what is now called his miracle year. In one of his papers, he presented what he modestly called "On the Electrodynamics of Moving Bodies," the work that would later be known as the special theory of relativity. Instead of trying to patch Newtonian physics with extra assumptions, Einstein began with 2 deceptively simple postulates. First, the laws of physics are the same for all observers moving at constant speeds relative to one another. There is no preferred frame of reference. Second, The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. At first glance, these statements seem harmless, but together they demand a profound rethinking of space and time. If the speed of light is fixed and the laws of physics are the same in all inertial frames, then the only way to reconcile these facts is to abandon the idea that space and time are separate, absolute entities. Instead, they must adjust themselves to preserve the constancy of light's speed. This adjustment is what we now recognize as the relativity of time and space. Einstein's logic was both simple and shocking. Imagine two observers, one standing still on a train platform, the other riding on a train moving at high speed. If a flash of light occurs midway between the front and back of the train, the observer on the train sees the light reach both ends simultaneously. But for the observer on the platform, the rear of the train is moving toward the point of the flash, while the front is moving away from it. To them, the light should reach the rear sooner than the front. Since both observers must measure the same speed for light, the only possible resolution is that they disagree on whether the two events, the light reaching the front and back, happened at the same time. Simultaneity itself becomes relative. From this simple realization follows a cascade of consequences. Time intervals and distances are not fixed quantities that all observers agree on. They depend on the relative motion between the observers. A moving clock runs slower relative to one at rest. A moving ruler measures shorter than one at rest. These are not illusions caused by measurement errors. They are intrinsic features of reality as described by relativity. Einstein's equations showed exactly how these effects depend on relative velocity. For speeds much less than the speed of light, the differences are tiny, too small to matter in everyday life. But as an object's speed approaches that of light, the differences grow dramatic. In the limit of moving at light speed, time would appear to stop entirely for that object from an outside perspective, though in reality, nothing with mass can reach that ultimate speed. What made Einstein's breakthrough so powerful was that it explained the Michelson-Morley result without invoking any mysterious ether. There was no hidden medium for light to travel through. Instead, space and time themselves formed the arena in which light moved, and that arena had properties far stranger than anyone had previously imagined. Light's constant speed was not an accident, but a fundamental feature of the geometry of space-time. It is worth emphasizing that Einstein did not merely propose a new philosophy of time. His theory made concrete predictions that could be tested. One such prediction was the time dilation effect on moving clocks. This was later confirmed in particle physics experiments, where unstable particles moving at high speeds live longer than identical particles at rest. It was also confirmed when highly precise atomic clocks were flown on airplanes and compared to those on the ground. The airborne clocks fell behind exactly as relativity predicted. The special theory of relativity deals only with observers moving at constant speeds relative to one another, without acceleration. But Einstein's work did not stop there. Within a decade, he extended his ideas to include acceleration and gravity in the general theory of relativity. In that broader framework, gravity itself is understood as the curvature of space-time, and time is affected not just by motion, but by the presence of mass and energy. That is the domain in which gravitational time dilation, the slowing of time in stronger gravitational fields, naturally emerges. But even in the special theory, stripped of gravity's complexities, the relativity of time is an astonishing shift in perspective. For centuries, we assumed that there was one master clock governing the universe, ticking away in perfect synchrony everywhere. Einstein showed us that this was an illusion. Every observer carries their own clock, and there is no absolute sense in which one is correct, and the others are wrong. The laws of physics care only about the relationships between these clocks, not about any universal timekeeper. This realization has profound consequences. It means that the sequence and timing of events can depend on your path through space-time. It means that the notion of a shared now across the cosmos is meaningless without specifying an observer's frame of reference. It also means that time is not something separate from the physical world. It is part of the fabric that matter and energy shape and are shaped by. In the years since Einstein's 1905 paper, relativity has become one of the most thoroughly tested theories in all of science. Its predictions have been confirmed in particle accelerators, in the timing of pulsars, in the operation of the global positioning system, and in countless other ways. Yet the core insight remains as startling today as it was more than a century ago. Time is not absolute. It is relative to motion and to the geometry of the universe itself. If there is an existential lesson to be drawn from this, it might be that our everyday sense of reality is only a narrow window into a far richer structure. We imagine ourselves all moving together through time, synchronized in the same moment. In truth, each of us carries our own personal thread through space-time, woven in ways that others cannot perfectly match. Somewhere out there in the vastness, another clock is already ahead of yours, another is behind, and neither is more real than the other. Time belongs to no one and to everyone, and in that quiet truth, we find both our individuality and our connection to the cosmos. Chapter 3. Moving through time at different speeds. In everyday life, time seems to flow at the same pace for everyone. Whether you are walking to the store, sitting in an office, or riding a train, you feel as though the seconds are slipping past in a steady rhythm. Clocks appear to agree with each other, and if there is any difference at all, it is small enough to be ignored. This common experience has shaped our intuitive sense of time for centuries. But physics shows us that this sense is incomplete. The flow of time is not uniform across all observers. How quickly time passes for you depends on how you move through space, and by extension, through space-time itself. In Einstein's framework, space and time are inseparable. They form a single four-dimensional continuum in which all events take place. Every object from a grain of dust to a galaxy follows a path through this continuum called a world line. The speed at which an object moves through space determines how it moves through time. In a deep and precise sense, all objects travel through space-time at the same overall rate, but the division between motion in space and motion in time shifts depending on the object's velocity. The faster you move through space, the less you move through time. This idea can be difficult to picture because our senses are not equipped to detect changes in the rate of time directly. If you were on a spaceship traveling close to the speed of light, your own clock would tick normally. Your heartbeat, your thoughts, the rhythm of your speech, all would feel exactly as they do now. But if someone back on Earth could somehow watch your clock as you flew past, they would see it ticking more slowly than theirs. If they could monitor your heart rate, they would see it slow. From their point of view, you would be living in slow motion. And the effect is mutual. From your perspective aboard the ship, it would be the people on Earth whose clocks run slow. Both points of view are valid. This symmetry is one of the most striking aspects of time dilation and special relativity. There is no universal right answer to the question of whose time is moving correctly. The only thing that matters is the relative motion between observers. This concept is famously illustrated by the so-called twin paradox. Imagine two identical twins. One remains on Earth, while the other sets off on a high-speed journey to a distant star and back. Upon returning, the traveling twin finds that less time has passed for them than for their sibling. Perhaps the earthbound twin has aged by 10 years, while the traveler has aged by only 6. Despite the name, there is no real paradox here. The resolution lies in the fact that the traveling twin must accelerate to turn around and come back, breaking the symmetry of motion between the two. But even without acceleration, the basic principle remains. Moving through space at high speed changes how you move through time. This is not mere speculation. Time dilation has been measured and confirmed in numerous experiments. One of the most elegant involves subatomic particles called muons. These particles are unstable, with a mean lifetime of about 2.2 millionths of a second when at rest. Produced high in Earth's atmosphere by cosmic rays, muons should decay long before they reach the surface. Yet many do reach the ground. The reason is that they are moving close to the speed of light, and in their own frame of reference, the time before they decay is unchanged. But from Earth's point of view, their internal clocks run slow, stretching their lifetimes enough for them to survive the journey. Laboratory experiments have reproduced this effect under controlled conditions. Physicists can create beams of fast-moving muons in particle accelerators and measure their lifetimes. Sure enough, the faster the muons move, the longer they live compared to their at-rest counterparts. The agreement between experiment and Einstein's predictions is exact, with no measurable deviation. A more down-to-earth example comes from experiments with atomic clocks. These devices are among the most accurate timekeepers ever built, able to measure time to within billionths of a second. In the 1970s, scientists placed synchronized atomic clocks on commercial airliners flying around the world, while identical clocks remained stationary in a laboratory. When the flying clocks were brought back, they were found to have lost tiny amounts of time compared to the stationary ones, exactly as special relativity predicts. The differences were small, mere billionths of a second, but they were real and measurable. In fact, modern technology must account for this effect. The global positioning system relies on satellites orbiting Earth, each carrying its own atomic clock. These satellites move at thousands of kilometers per hour relative to the ground, and their clocks tick more slowly because of time dilation. At the same time, they are farther from Earth's surface and experience weaker gravity, which causes their clocks to tick faster due to gravitational time dilation. The combination of these two effects must be precisely calculated and corrected for. Without these adjustments, GPS would accumulate navigation errors of several kilometers each day. That our devices can guide us within a few meters is a testament to the accuracy of Einstein's theory. These real-world demonstrations make it clear that time dilation is not a theoretical oddity, but a fundamental feature of the universe. When you move quickly relative to someone else, you are quite literally moving through time at a different pace. The effect is negligible at the walking speeds and car speeds of daily life, but it grows rapidly as you approach the speed of light. At 99% of that ultimate speed limit, time for you would run at less than half the rate experienced by someone at rest. Push the speed higher still, and the effect becomes even more dramatic. It is sometimes said that a spaceship capable of near-light travel could serve as a one-way ticket to the future. By accelerating to such speeds, a traveler could journey across the galaxy in what feels like a few years of personal time, only to find that centuries have passed on Earth. Science fiction has explored this idea for decades, and while the engineering challenges are immense, the physics behind it is sound. In this way, relativity offers a form of time travel, one that moves only forward, but as far forward as you like, depending on how fast you can go. This also means that time dilation is an inseparable aspect of space exploration at relativistic speeds. Any human mission that approached a significant fraction of the speed of light would return to an Earth much older than the crew. For the astronauts, their subjective experience of the voyage might be short, but they would come back to a planet that had changed beyond recognition. This is not a philosophical idea, but a mathematical certainty grounded in experimental fact. It is worth noting that time dilation does not involve any distortion of the traveler's own experience. To them, their clock runs normally, their heartbeat is steady, and their conversations unfold at the usual pace. The slowing down happens only relative to another observer in a different frame of motion. This is why the effect can be so counterintuitive. We are used to thinking of time as something we all share in common. But in reality, each of us carries our own personal version of it, shaped by our unique trajectory through space-time. In this sense, motion through space is a kind of trade-off with motion through time. When you are at rest, all your motion is through time. As you move faster through space, less of your total motion is in the time direction. This trade-off is invisible to us at ordinary speeds, but it becomes unavoidable near the cosmic speed limit. Photons, the particles of light, are an extreme example. They move at the speed of light through space and not at all through time. From their point of view, if such a point of view could be meaningfully defined, no time passes at all between being emitted and being absorbed. This interplay between space and time underscores the unity of space-time. We cannot change how fast time flows for us in an absolute sense, but by moving differently relative to others, we change how our time compares to theirs. Each observer's experience is internally consistent, yet different from every other's. This is why relativity is as much a revolution in perspective as it is in mathematics. Understanding this makes the universe feel both more strange and more connected. The notion that you could travel for what feels like a year and return to find that decades or centuries have passed elsewhere is not science fiction fantasy. It is a built-in feature of the way reality works. And this feature holds whether you are a muon in the upper atmosphere, an astronaut in orbit, or a hypothetical traveler skimming the edge of light speed. We live our daily lives far from these extremes, yet we are all moving through space-time at our own pace. No two clocks in the universe tick exactly alike, because no two share exactly the same motion or location in gravity's field. In a quiet way, we are all travelers through time, each following a unique path. And though our differences are small, they are real. A reminder that even something as familiar as the passing of seconds holds within it the deep and subtle structure of the cosmos. Chapter 4. Gravity's Grip on Time. It is natural to think of gravity as a force that pulls things down. Drop an apple and it falls to the ground. Release a stone above a pond and it plummets into the water. This is the gravity of everyday life. A steady, invisible hand that anchors us to earth. For centuries, this picture was the foundation of our understanding. Newton described gravity as a universal attraction between masses, acting instantly across empty space. It was powerful and accurate enough to predict the motion of planets and the return of comets. But in Newton's world, time was untouched by gravity. No matter where you were, the seconds ticked away at the same universal rate. Einstein changed this view completely. In his general theory of relativity, published in 1915, gravity is not a force in the Newtonian sense. Instead, it is the manifestation of space-time curvature. Massive objects like planets, stars, and black holes deform the geometry of space-time around them. Other objects, and even light itself, move along paths dictated by this curvature. The result is that what we perceive as gravitational attraction is actually motion through a warped space-time landscape. One of the most surprising consequences of this new understanding is that gravity affects time itself. The stronger the gravitational field you are in, the slower time runs for you relative to someone farther from that source of gravity. This is not a matter of perception, nor is it caused by the physical stress of being in a gravitational field. It is a direct result of the way space-time geometry works. Just as gravity bends the paths of moving objects, it bends the path that time itself follows. To visualize this, imagine space-time as a vast, flexible surface. A massive object like Earth creates a dent in that surface, curving it inward. Clocks placed at different depths in that curvature tick at different rates. A clock closer to the mass, deeper in the gravitational well, runs more slowly than one farther away. This is gravitational time dilation. The effect is subtle in our daily lives. On Earth, the difference between a clock at sea level and one at the top of Mount Everest is tiny but measurable. Experiments with precise atomic clocks have confirmed this repeatedly. In one famous experiment in 2010, researchers placed one atomic clock on the floor and another just 33 centimeters higher. Even over such a small height difference, the clock closer to the ground, experiencing slightly stronger gravity, ticked more slowly than the higher one. The difference was only a few parts in 100 trillion, but it was real, exactly as predicted by general relativity. The same principle applies on larger scales. A satellite in orbit is farther from Earth's center and feels weaker gravity, so its clock ticks slightly faster than clocks on the ground. This effect is combined with the special relativistic time dilation caused by the satellite's speed, and both must be accounted for in systems like GPS. Without correcting for gravitational time dilation, GPS errors would grow by about 10 kilometers each day. The fact that our navigation devices work at all is a daily, silent confirmation that Einstein was right. Gravitational time dilation becomes far more dramatic near extremely massive and compact objects. Consider a neutron star, the collapsed core of a massive star, with a mass greater than the Sun's, packed into a sphere only about 20 kilometers wide. The gravitational field at its surface is billions of times stronger than on Earth. A clock placed there would tick far more slowly compared to one far away in interstellar space. From the perspective of a distant observer, any process on the neutron star, the ticking of a clock, the beating of a heart, even the decay of radioactive atoms, would appear to proceed at a glacial pace. And then there are black holes, the ultimate demonstration of gravity's effect on time. A black hole's mass is concentrated in a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which nothing can escape. As you approach the event horizon from a safe distance, gravitational time dilation grows more and more extreme. To an outside observer watching from far away, Your approach seems to slow. Your clock ticks ever more sluggishly. In the final moments before crossing the event horizon, your movement appears to freeze. Light from you becomes increasingly redshifted, stretched to longer and longer wavelengths until it fades from view entirely. From your own perspective, however, nothing unusual happens to your clock. Time flows normally for you as you cross the horizon. But the rest of the universe races ahead, possibly by millions or billions of years, depending on the black hole's size and the details of your trajectory. This extreme warping of time is not just a theoretical curiosity. Astronomers can see its effects in the light coming from matter near black holes. As gas spirals inward in an accretion disk, its emitted light is gravitationally redshifted, a direct fingerprint of time running differently in the intense gravity near the event horizon. These observations match the predictions of general relativity with extraordinary precision. Einstein's equations show that gravitational time dilation is a universal feature of space-time. It is not confined to black holes or neutron stars. It happens everywhere there is mass, which means everywhere in the universe. Even Earth's modest gravity stretches time ever so slightly, enough for sensitive instruments to measure it. This universality is part of what makes general relativity so powerful. The same mathematics describes the tiny difference between two clocks a meter apart and the staggering slowdown near a black hole. From a practical standpoint, accounting for gravitational time dilation is essential in many areas of science and technology. In satellite navigation, in precision geodesy, in the operation of deep space probes, the effects of gravity on time are as real as the pull of gravity on a falling object. The equations that predict planetary orbits also predict the way time itself is bent by gravity. They are two sides of the same underlying geometry. It is striking to realize that gravity, which we experience so casually every day, is quietly altering the pace of time for us and everything around us. The difference is too small to feel, but it is there. You age ever so slightly more slowly at sea level than you would on a mountaintop. A pilot flying at high altitude ages a fraction more than someone sitting in an airport cafe. And if you could spend years near the surface of a neutron star without being crushed by its gravity, you could return to find that entire epochs had passed elsewhere. In this way, gravitational time dilation offers another route to what might be called time travel into the future. By living in a region of stronger gravity, you move more slowly through time compared to those in weaker gravity. Science fiction often imagines enormous time jumps achieved through high-speed spaceflight, but they could equally well be achieved by parking yourself near a compact, massive object. Of course, in practice, the dangers of such environments make this a far less appealing option. There is something humbling in the realization that time is not the same everywhere. In the vast cosmic web of galaxies and stars, every region has its own pace, set by its motion and by the gravitational landscape it inhabits. The universe is not synchronized by a single master clock. Instead, it is a patchwork of times, each tied to its own place in spacetime's curvature. We are part of that patchwork, bound to Earth's gravity, moving through our own slightly slowed version of time. From a distance, the differences are tiny for most of us, but they are real and measurable. They remind us that time is not the fixed, unchanging backdrop we once thought it to be. It is pliable, influenced by mass and energy, bent by gravity into different shapes for different observers. Our everyday sense of time's universality is a useful approximation, but it hides the deeper truth that time itself is part of the gravitational fabric of the cosmos. And here, perhaps, lies the most unsettling and beautiful thought of all. Each of us lives in our own private river of time, flowing at a pace shaped by where we are and how we move. Two people standing side by side are almost perfectly synchronized, yet not entirely. Somewhere out there, deep in the heart of a galaxy, near the crushing pull of a black hole, someone else's river runs far more slowly. And all these rivers flow together into the vast, uncharted ocean of space-time, a place where the seconds of one world may be the centuries of another. Chapter 5. Time Dilation in Everyday Technology. For most people, time dilation sounds like something distant, a phenomenon that belongs to the realm of high-energy physics experiments, deep space travel, or the extreme gravity near a black hole. But the truth is more surprising. Time dilation is part of the everyday infrastructure that quietly underpins modern life. It is not a theoretical curiosity you might only encounter in a physics classroom. It is a measurable effect that engineers, scientists, and technicians must account for if they want our technology to work correctly. Without the corrections dictated by relativity, some of the tools we rely on every day would quickly drift into uselessness. One of the most striking examples is the Global Positioning System. GPS is a network of satellites orbiting Earth at an altitude of roughly 20,000 kilometers. Each satellite carries multiple atomic clocks, which are among the most accurate timekeeping devices ever made. These clocks broadcast signals containing the precise time and the satellite's position. A GPS receiver, whether in a car, a smartphone, or a ship's navigation system, calculates its own position by comparing the arrival times of signals from at least 4 satellites. The calculation is essentially a timing problem. By knowing how long the signal took to arrive and the constant speed of light, the receiver can determine its distance from each satellite and thus pinpoint its location. This process depends critically on the synchronization of the satellite clocks with clocks on the ground. If the timing is off by even a few billionths of a second, the resulting position error can be tens or hundreds of meters. That might not matter much when looking at a map on a casual walk, but for navigation in aviation, shipping, or military operations, such errors could be disastrous. And here is where relativity steps in. The satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface. According to special relativity, a moving clock ticks more slowly than one at rest relative to the observer. This causes the satellite clocks to lose about 7 microseconds per day relative to those on Earth. At the same time, because the satellites are farther from Earth's center, they experience weaker gravity. General relativity tells us that clocks in weaker gravity run faster, and in this case, the effect is stronger than the velocity-based slowdown. The reduced gravity speeds up the satellite clocks by about 45 microseconds per day. When both effects are combined, the net result is that satellite clocks tick about 38 microseconds faster per day than clocks on the ground. A difference of 38 microseconds might not sound like much, but light travels about 11 kilometers in that time. Without correcting for this difference, GPS positions would drift by roughly 10 kilometers each day. That level of inaccuracy would make GPS useless for navigation. Engineers solve the problem by pre-adjusting the satellite clocks before launch so that when time dilation effects are taken into account, they remain synchronized with ground-based time. In addition, the system constantly monitors and corrects for tiny variations that arise from other factors, such as changes in satellite orbits and temperature fluctuations affecting clock performance. GPS is perhaps the most widely known technological application where time dilation must be considered, but it is far from the only one. Modern communications networks, the global web of fiber optic cables, satellites, and switching stations, rely on precise timing to coordinate data transfer. Financial markets use high-frequency trading systems that depend on timestamps accurate to billionths of a second to determine the order of trades. In such systems, even small timing errors can have significant financial consequences. The synchronization of these systems across different locations on Earth must account for relativistic effects, especially when satellites are involved in the transfer of timing signals. Scientific research also depends heavily on an understanding of time dilation. Large-scale particle accelerators, such as the Large Hadron Collider, push particles to speeds approaching the speed of light. In these environments, time dilation is no longer a subtle effect. It becomes essential to interpreting experimental results. As particles move faster, their internal clocks, such as the processes governing their decay, slow down relative to the laboratory frame. By measuring these lifetimes and comparing them with those predicted by relativity, scientists confirm the theory's accuracy to extraordinary precision. In this way, high-energy physics is both a user and a tester of time dilation. Relativity also plays a role in astronomy. Observations from spacecraft traveling through the solar system must account for the time dilation effects of both their motion and their position in the sun's gravitational field. Signals from distant probes, such as those from the Voyager spacecraft, must be interpreted with these corrections in mind to ensure accurate tracking and navigation. When scientists time the arrival of pulses from distant pulsars, rotating neutron stars that emit regular radio bursts, they must include relativistic corrections if they want to measure positions, distances, and velocities accurately. Even in metrology, the science of measurement, time dilation is part of everyday work. Laboratories that maintain national time standards keep their atomic clocks in constant comparison with international counterparts. These comparisons require detailed corrections for the effects of both gravitational and velocity-based time dilation. A clock on a mountaintop will tick at a measurably different rate from one at sea level, and both will differ slightly from clocks in orbit. By carefully accounting for these effects, scientists can keep coordinated universal time, the global time standard, synchronized across the planet. These examples reveal a simple truth: time dilation is woven into the infrastructure of the modern world. We do not notice it because we live in a society that has quietly built Einstein's corrections into its systems. When your phone maps a route to a restaurant, it is relying on equations born from special and general relativity. When you stream a video via satellite internet, those signals are being timed and synchronized with relativistic corrections. When a spacecraft lands on Mars, its navigation is guided by systems that would fail without accounting for the bending and stretching of time. This should be a humbling realization. In Newton's day, time was thought to be uniform and absolute, a background on which the events of the universe played out. Today, our everyday technology depends on the understanding that this is not true. Time is not the same everywhere, and its variations matter. Enough to shift your navigation by kilometers, enough to confuse a global financial network, enough to alter the lifetime of a particle whirling inside a collider. If anything, the quiet presence of time dilation in technology is a reminder of how deeply the universe's subtle structure permeates our lives. We often imagine fundamental physics as something remote from daily concerns, hidden away in observatories or research laboratories. But in truth, the principles uncovered by Einstein more than a century ago operate in the background of almost everything we do. They are there when an aircraft's navigation system finds its way through the clouds, when a container ship charts a course across the Pacific, when a rescue team uses GPS to locate a missing hiker. It also reframes how we think about progress. We tend to see technology as the driver of scientific understanding, as if new machines push science forward. But here, the flow runs both ways. The abstract insights of relativity, once thought of as purely theoretical, became indispensable tools for building the interconnected world. Physics is not just the domain of distant stars and subatomic particles. It is in your pocket, guiding your steps through a city. And there is another, quieter thought. We live inside a framework where time itself is elastic, where every clock in the sky, on the ground, on a mountaintop, in a satellite, keeps its own subtly unique beat. Our technology forces these differences to align, to create the illusion of a single, shared time. But beneath that illusion, the diversity of time's flow remains, an unspoken feature of reality that even the simplest phone navigation depends on. Every time your location is updated, you are unknowingly making use of a fact about the universe that says, your time is not the same as mine, and neither of us measures the same time as a clock circling overhead. In this way, relativity lives with us constantly, whether we are aware of it or not. It is the invisible hand on the systems we trust, the quiet adjustment in the background that keeps our digital lives in step with the cosmos. And perhaps, knowing this, we can feel a little more connected to the larger universe, not as passive observers, but as active participants, moving within its warped and beautiful fabric. Chapter 6. Falling into the slowest time in the universe. In the vastness of the cosmos, most places share roughly the same rhythm of time. Whether you stand on the surface of a quiet moon, float between the stars, or orbit a familiar planet, the seconds flow in a steady, almost indistinguishable beat. The differences are there, subtle and measurable, but they do not define your everyday reality. Yet there are regions of the universe where this rhythm breaks down, where time slows to an unimaginable crawl. These are the domains of the strongest gravitational fields, the places where space itself curves so steeply that even light struggles to escape. Here, time dilation is not a small correction to a clock's tick, but a defining feature of existence. And the slowest time in the universe belongs to the neighborhood of a black hole. Black holes are the most extreme consequence of Einstein's general theory of relativity. They are regions where matter has collapsed beyond the point where it can resist its own gravity. The mass is concentrated into an infinitely dense point called a singularity, surrounded by an invisible boundary known as the event horizon. The event horizon is not a physical surface you could touch. Instead, it is the limit at which escape velocity equals the speed of light. Beyond it, no signal, no matter, no light can return. What lies inside remains forever hidden from the rest of the universe. From far away, a black hole may seem deceptively ordinary. If you orbited one at a safe distance, your experience would not be so different from orbiting any other massive object of comparable mass. But as you approach, the pull of gravity grows rapidly, and the curvature of space-time becomes more severe. And with that curvature comes an equally dramatic warping of time. To understand what happens, imagine lowering a clock toward a black hole. From your safe vantage point far away, you watch as the clock descends. As it nears the event horizon, you see its ticks grow farther and farther apart. At first, the change is small, almost imperceptible, but as the clock approaches the horizon, the effect intensifies. Each second on that falling clock seems to take longer to arrive. The light carrying the image of the clock becomes stretched, its color shifting toward the red end of the spectrum, a gravitational redshift caused by the intense warping of space-time. The closer the clock gets to the event horizon, the slower it appears to run, until in the final moments it seems to freeze altogether. From your perspective, time for that clock has stopped. This effect is not an illusion in the sense of being a trick of the eye. It is a direct consequence of the geometry of space-time near a black hole. Your observations are entirely consistent with the mathematics of general relativity. For you, the outside observer, it will always take an infinite amount of time for the clock, or any object, to actually cross the event horizon. This is why, in a sense, the black hole's surface is never truly seen to be crossed by anything in real time. But for the clock itself, and for anything falling with it, the experience is completely different. In its own frame of reference, time flows normally. The clock ticks in steady rhythm, seconds passing just as they do on Earth. A falling astronaut would feel no sudden slowing of time as they cross the event horizon. They might notice the outside universe speeding up in a surreal way, but their own experience would be continuous. The paradox is only apparent. It is the relativity of time made visible in its most extreme form. The closer you get to the singularity, the steeper the gravitational well becomes. In this region, tidal force, the differences in gravitational pull between your head and your feet, can grow immense. For stellar mass black holes, these tidal forces would stretch and compress you violently, a process sometimes called spaghettification. For supermassive black holes, such as those at the centers of galaxies, the tidal forces near the event horizon are much weaker, and you might cross without immediate physical harm. But the slowing of time relative to the outside universe would still be extreme. If you could somehow hover just above the event horizon, supported by a hypothetical engine or tether, your clock would run incomprehensibly slower than clocks in interstellar space. A few hours for you might correspond to centuries, millennia, or more for someone far from the black hole. The outside universe would change in a blur. Stars would evolve, galaxies would drift, entire civilizations could rise and fall while you experience the passage of only a short personal time. This is not merely a thought experiment. Astronomers see evidence of gravitational time dilation in the real universe. In the accretion disks around black holes, matter spirals inward, heating up and emitting intense radiation before it crosses the event horizon. The light from this matter is redshifted by gravity, a signal that the time near the black hole is running more slowly relative to our own. In some cases, we can even use this effect to estimate the black hole's mass and spin. One of the most famous fictional depictions of this effect appeared in the film Interstellar, in a scene where astronauts land on a planet orbiting close to a supermassive black hole. Due to the intense gravity, time on the planet is slowed so much that an hour there corresponds to 7 years for the crew's colleagues waiting farther away. While the film's exact numbers are stylized for drama, the underlying physics is correct in principle. A sufficiently close orbit around a massive black hole would indeed produce such enormous time differences. The mathematics behind gravitational time dilation near a black hole is precise, but its implications are vast. For example, consider the possibility of using such an environment for one-way travel into the far future. If you could orbit just outside the event horizon for a few months of your own time and then return to a safe distance, you might find that decades, centuries, or longer had passed in the wider universe. While this is far beyond our current technology and fraught with deadly challenges, it remains a genuine prediction of relativity. The slowest clocks in the universe, then, are not in human laboratories or orbiting satellites. They are deep in gravitational wells at the very edge of black holes. And the idea that time can all but stop relative to the rest of the cosmos forces us to rethink our intuitive sense of now. There is no universal present that applies everywhere. In the shadow of a black hole, now is stretched almost beyond recognition. In this context, time dilation is not a minor detail. It is central to how black holes interact with the universe. It shapes the way they accrete matter, how they appear to observers, how they affect surrounding stars. Even the famous concept of Hawking radiation, the slow leakage of particles from black holes predicted by quantum theory, must be understood against the backdrop of the strange way time behaves at the horizon. If you stand far from any black hole, it is easy to imagine that the seconds you count are the same seconds ticking in all corners of the cosmos. But this is a comforting illusion. Out there in the deepest wells of gravity, time is crawling almost to a standstill. A photon of light climbing out of such a place stretches and fades, carrying with it a silent record of the slower pace from which it came. It is tempting to imagine what it would feel like to live in such a place, not just to visit briefly, but to experience life with the rest of the universe racing ahead. Perhaps your world would seem unchanged, while the stars in the night sky shifted from week to week, and the constellations you knew twisted into new patterns. You might watch galaxies drift perceptibly in the sky, a cosmic ballet sped up beyond anything we can see from Earth. And yet for you, the days would pass as they always have. In these extreme realms, we are reminded that time is not an absolute river flowing at the same pace everywhere. It is a local phenomenon, a rhythm that depends on where you are in the geometry of space-time. The slowest time in the universe belongs to the deepest pockets of gravity, where the curvature of space-time bends clocks almost to stillness. And in those places, the future of the universe unfolds at dizzying speed, but only for those who watch from afar. It is an extraordinary thing to realize that such regions exist, perhaps in the centers of most galaxies, quietly shaping the flow of time in their surroundings. They are not simply exotic astrophysical objects. They are reminders that the cosmos is a place where even the most basic aspects of reality, the order and pace of moments themselves, are not fixed, but molded by the invisible architecture of space-time. And perhaps in the quiet moments when we think of such places, there is a deeper reflection to be found. We tend to think of our time as the only measure of our lives, but the universe holds countless other clocks, each beating to its own gravitational rhythm. Somewhere near the edge of a black hole, a second lasts almost forever, and in that stretched-out moment, the rest of the cosmos rushes on without pause. Chapter 7. Cosmic Time Machines. Is time travel possible? The idea of traveling through time has fascinated humanity for centuries. Long before the equations of relativity, stories were told of people who awoke to find that years had passed in what felt like a single night, or who wandered into hidden realms where time flowed differently. In the modern imagination, time travel has become a staple of science fiction, a narrative device that lets us visit ancient civilizations, witness the birth of the stars, or correct mistakes from our own past. But behind the storytelling lies a genuine scientific question. Is time travel physically possible? In one sense, the answer is already yes. Every one of us is traveling through time right now, advancing into the future at a steady pace of 1 second per second. Relativity extends this by showing that the rate at which we move into the future is not fixed. We have already seen that velocity and gravity can change how fast time passes for us relative to others. This is not theoretical. It has been measured countless times in laboratories, in satellites, in high-speed particles, and in the precise signals from GPS systems. If you can move fast enough or spend time in a region of strong gravity, you can slow your own clock compared to those who remain behind. When you return, more time will have passed for them than for you. In this way, relativity allows a kind of one-way time travel into the future. We have also seen, in the context of black holes and high-speed journeys, that such effects could, in principle, be extreme. A sufficiently fast spaceship could take you on a journey lasting a few years by your clock, while centuries passed on Earth. A carefully chosen orbit near a supermassive black hole could allow you to experience hours while decades unfolded elsewhere. These are not speculative fantasies, but direct consequences of relativity. They would require enormous energy and extraordinary engineering, but the underlying physics is sound. What about travel to the past? This is where the science becomes far more uncertain. The equations of relativity do not outright forbid the idea, but they make it extremely difficult to achieve in any physically reasonable way. General relativity admits solutions to its equations in which closed time-like curves exist, paths through space-time that loop back on themselves. Following such a path, an object could, in principle, return event in its own past. But these solutions tend to involve conditions or structures that may not exist in our universe, or that require forms of matter and energy that violate known physical laws. One such theoretical structure is the wormhole, a hypothetical tunnel connecting two distant points in spacetime. If wormholes exist and could be stabilized, they might allow rapid travel between their endpoints. In certain configurations, they could also function as time machines. If one mouth of the wormhole were moved at high speed or placed in a strong gravitational field, time would pass differently for it than for the other mouth. Upon reuniting the mouths, a traveler entering one side could emerge from the other at an earlier time. This is a straightforward application of time dilation to a hypothetical shortcut through spacetime. But wormholes come with daunting challenges. Even if they exist, keeping them open would require exotic matter with negative energy density, something not yet observed in usable quantities. Quantum field theory suggests that such negative energy can appear in small amounts for brief times, but whether it can be harnessed to stabilize a wormhole remains speculative. And even if these obstacles were overcome, questions about stability, causality, and quantum effects near the wormhole mouths remain unsolved. Another class of solutions involves rotating universes or massive rotating cylinders, such as the Gödel universe model. In these spacetimes, the geometry can permit closed time-like curves without exotic matter. But these models generally do not match the observed properties of our universe, and they often require unrealistic conditions, such as an infinitely long cylinder of extremely dense material. Even if a stable past-traveling time machine could be built in principle, physics raises further difficulties. Quantum field effects in curved spacetime suggest that attempts to create such a device might trigger enormous energy feedbacks, destroying the time machine as soon as it formed. This is sometimes called the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics may conspire to prevent time travel to the past. While this remains unproven, it aligns with the absence of evidence for visitors from the future. Philosophically, travel to the past also raises deep questions about causality, the principle that causes precede effects. If you can visit your own past, could you change it? If you prevent an event from happening, what becomes of your reason for going back? These logical puzzles, often framed as paradoxes, hint at the complexity of allowing backward time travel in a consistent universe. One way physicists sometimes sidestep these paradoxes is through the idea of self-consistency. The universe might permit past travel, but only if events unfold in ways that do not change history. In this view, any actions you take in the past were always part of history to begin with. Another resolution comes from the many worlds interpretation of quantum mechanics, in which different outcomes of events exist in separate, branching universes. In this framework, traveling to the past might place you in a different branch of history rather than altering your own. But this moves the question into the territory of quantum cosmology, where experimental evidence is scarce and theory is still evolving. It is important to note that even without past travel, relativity already makes our universe a kind of cosmic time machine. The combination of high-speed motion and strong gravity can, in principle, move you arbitrarily far into the future of others. If you wanted to see the far future of Earth without living through the intervening centuries, the laws of physics offer ways to do it, though they are far beyond our current technology. Such journeys would not change the past, but they would alter your relationship to it, severing your direct connection to the time you left behind. In a way, this future-only time travel is the safer, more consistent form. It avoids paradoxes and fits neatly within our current understanding of physics. It also connects naturally with the idea that all of us are already moving into the future at our own rates. By controlling the conditions, speed, gravity, and trajectory, we could, in theory, choose how far ahead we wish to leap. The dream of moving freely through time in either direction continues to inspire research, not because physicists expect to build a time machine next year, but because studying the limits of what is possible deepens our understanding of space-time. Investigating whether wormholes can exist, whether quantum effects enforce chronology protection, and how causality emerges from the laws of physics helps refine our theories and may even reveal new connections between gravity and quantum mechanics. And yet, beyond the mathematics and engineering challenges, there is something more elemental at work. Time travel, whether forward or backward, forces us to confront our place in the unfolding of events. If the past is fixed and the future open, what does it mean to alter one's path through time? If the universe is a block where all events coexist, is travel just another way of saying we experience different parts of it? These questions touch the boundary between physics and philosophy, where the language of equations meets the language of meaning. Ultimately, whether or not we ever build a literal time machine, relativity has already shown us that time is not the uniform backdrop we once imagined. It bends, stretches, and curves with the geometry of the universe, allowing travelers to experience it differently. In this sense, the universe itself is our time machine, one we are riding every moment of our lives. Perhaps this is the quiet truth hidden behind the grander fantasies of science fiction. We are all time travelers already, each on a unique trajectory shaped by our motion, our gravity, and our choices. Some paths run almost parallel, keeping us close to those we know. Others diverge sharply, carrying us far from the rhythms of others' lives. And somewhere out there, among the stars and black holes, the slowest and fastest clocks in the cosmos are keeping their own silent time, marking out the infinite variety of journeys through the ever-changing landscape of space-time. Chapter 8. The Universe's Many Clocks. If you could stand outside the universe and listen to it as if it were a great cosmic machine, you might expect to hear a single steady tick, a universal heartbeat shared by all matter and all events. But the deeper we look into the nature of time, the more we see that such a rhythm does not exist. Instead, the universe is filled with countless clocks, each ticking at its own pace, each marking the passage of time along its own unique path through space-time. There is no master clock that keeps them all in step, no central metronome that sets the tempo for existence. The rhythm of time is local, personal, and deeply dependent on where you are and how you move. In physics, a clock can be almost anything that measures change in a predictable way. It could be the oscillation of atoms in an atomic clock, the swing of a pendulum, the vibration of a crystal, the rotation of a pulsar, or even the decay of a radioactive isotope. Each of these is a physical process that can be counted, and from that count, we can infer the passage of time. In a Newtonian world, all such clocks could be synchronized perfectly, provided they were built well enough and compared often enough. In our actual universe, as described by relativity, such perfect agreement is impossible. Relativity teaches us that the rate at which a clock ticks depends on its path through space-time, its world line. A clock deep in a gravitational well will tick more slowly than one far from any massive object. A clock moving at high speed relative to another will also tick more slowly from the other's perspective. These effects are not illusions or malfunctions. They are consequences of the geometry of space-time itself. And because every object in the universe follows its own path through that geometry, every clock has its own story. Consider the clocks on Earth alone. A clock at sea level is deeper in Earth's gravitational field than one on a mountain peak, and so, according to general relativity, it ticks more slowly. The difference is tiny but measurable with modern instruments. If you placed an atomic clock at the top of a tall skyscraper and another identical clock in the basement and let them run for a year, the clock upstairs would end up slightly ahead. The difference would be on the order of billionths of a second, negligible for human experience but vital for precise physics. Now widen your view to include the entire planet. The Earth is rotating, so points near the equator move faster than points near the poles. From the perspective of special relativity, this motion causes an additional time dilation. Combining the gravitational and rotational effects, we find that no two clocks on Earth tick exactly the same, unless they are in the same place and moving in the same way. Coordinated universal time, the standard we use to keep civil time, is maintained by averaging the readings of hundreds of atomic clocks around the world, with careful corrections for these relativistic effects. The differences become more dramatic beyond Earth. A clock on the moon, in weaker gravity and moving at a different speed around the sun, would drift relative to one on Earth. A clock on Mars would follow yet another tempo, shaped by Mars's mass, radius, and orbital motion. In interplanetary navigation, these differences must be calculated and compensated for, or spacecraft tracking would quickly lose accuracy. In deep space, the variety grows richer still. A pulsar, a rapidly rotating neutron star, is a kind of natural clock, its beams sweeping past our telescopes with astonishing regularity. The timing of these pulses can be measured to millionths of a second, but even they are subject to relativistic influences. A pulsar in a binary system orbiting another massive star will have its ticking rhythm altered by the gravitational field of its companion. As it moves toward us and away from us in its orbit, the special relativistic Doppler effect further changes the apparent timing of its pulses. By studying these variations, astronomers can not only confirm the predictions of relativity, but also weigh the stars, map their orbits, and test theories of gravity. Even the sun itself is a clock of sorts. The fusion reactions in its core proceed at a steady rate, setting the pace for the light and heat that reach Earth. But the sun's own clock is affected by its position in the Milky Way's gravitational field, by its motion through the galaxy, and by the immense gravitational pull of the galaxy's mass. From the standpoint of relativity, the sun's clock is no more universal than any other. If we turn our attention to the galaxy as a whole, we find that stars in different regions live in different temporal environments. Near the galactic center, the gravitational field is stronger, and time runs slightly more slowly relative to the galaxy's outskirts. A star orbiting close to a supermassive black hole experiences a different pace of time than one drifting in the thin halo far above the galactic plane. The differences are small on a human scale, but significant over cosmic ages. All of these variations are bound by one rule. Each clock is correct in its own frame of reference. There is no sense in which one is truly ahead or behind, in any absolute way. If two observers meet and compare clocks after following different paths through space-time, their readings may differ, but both are right. The disagreement is not a matter of error, it is a matter of geometry. This multiplicity of times can be disorienting because it runs against our everyday intuition. We are used to the idea that events happen at the same time in different places. Relativity tells us that simultaneity is relative, that two events judged simultaneous in one frame may occur at different times in another. This is not just a philosophical twist, but a measurable reality, confirmed in experiments and required for technologies like GPS to function. If we imagine the universe as a vast web of world lines, the paths of all particles and objects through space-time, then each point along each line carries its own local time. These times are linked by the structure of space-time, but they are not synchronized by any overarching clock. Instead, they form a patchwork, a mosaic of rhythms, each as real as the next. We can think of this mosaic as a kind of cosmic music. Each clock is an instrument playing its own part, shaped by its environment and motion. Some tick slowly in deep gravitational wells, others more quickly in the openness of intergalactic space. From a distance, their tempos might seem to blend into a background hum, but up close, each has its own distinct beat. There is beauty in this diversity, a reminder that the universe's unity is not the sameness of a rigid grid, but the harmony of many variations. On a practical level, the recognition of many clocks is essential for modern science. In space exploration, in astronomy, and fundamental physics, accurate timekeeping requires careful accounting of relativistic effects. Ignoring them would mean losing precision, misunderstanding signals, and misinterpreting data. But beyond its utility, the concept reshapes our philosophical picture of time itself. Time is not a single universal stream. It is a network of local flows, connected yet distinct, shaped by the curvature and motion of the cosmos. And there is an existential dimension to this realization. We live our lives inside one tiny thread of the cosmic tapestry, measuring time with the clocks of our world, and imagining that all others match ours. But in truth, every star, every planet, every particle moves to its own time. The universe is not a chorus of identical voices, but a symphony of endless variations. Somewhere, far away, a clock may be ticking slower or faster than ours, but both are equally part of the universe's story. And as we go about our days, unaware of the infinite diversity of time's flow, we are still part of that grand, intricate rhythm, one beat among countless others in the vast and beautiful score of space-time. Chapter 9. Does time itself flow, or do we just experience it that way? For most of us, the flow of time feels as real as the ground beneath our feet. We sense the moments sliding past, one after another, carrying us from the cradle to the present and on toward whatever lies ahead. Our entire mental life is embedded in this sense of passage, a constant forward movement from past to future. And yet, when we look at the world through the lens of modern physics, this familiar intuition becomes less certain. Does time truly flow in the way we imagine, or is that flow a feature of our perception rather than of the universe itself? In everyday life, we take time to be directional. We remember the past but not the future. We can act now in ways that influence what will happen, but we cannot act to change what has already occurred. This asymmetry is woven into our language, our thinking, and our sense of causality. Physics, however, paints a more ambiguous picture. The fundamental equations that govern the motion of particles, whether in classical mechanics, relativity, or quantum theory, are almost entirely time-symmetric. That is, they work equally well whether time runs forward or backward. If you were shown a film of two billiard balls colliding and had no other information, you could run it forward or backward and the laws of physics would be satisfied in either case. At the most fundamental level, nature's rules do not appear to distinguish between past and future. Where, then, does our sense of time's arrow come from? One answer lies in the concept of entropy, a measure of disorder or the number of possible microscopic configurations of a system. The second law of thermodynamics tells us that, in an isolated system, entropy tends to increase over time. A neatly stacked pile of papers can fall into disarray, but the reverse will not happen spontaneously. Eggs break, but do not unbreak. This increase of entropy defines a preferred direction for processes, from lower entropy to higher entropy. This is often called the thermodynamic arrow of time, and it is the closest thing we have to a physical explanation for why time seems to move in one direction. But even this explanation comes with subtleties. The laws that govern individual particles do not force entropy to increase. It is the statistical behavior of large numbers of particles that makes it overwhelmingly likely. The thermodynamic arrow is therefore not a fundamental law in the same sense as relativity's equations. It is an emergent property arising from the overwhelmingly probable behavior of complex systems given their initial conditions. If the universe had begun in a high entropy state, there would be no thermodynamic arrow at all, and time's direction might be imperceptible. Relativity complicates the picture even further. In Einstein's view, space and time form a four-dimensional continuum called spacetime. Every event, every location in space at a particular moment can be represented as a point in this continuum. Once an event has happened, it is fixed in spacetime, just as a mountain peak is fixed in a landscape. From this perspective, all moments, past, present, and future, exist equally as parts of the structure of spacetime. This is sometimes called the block universe or eternalism. In such a view, the passage of time is not a property of the external world, but a feature of our consciousness moving along our own world line. If the block universe is correct, then now is not a universal feature of reality. It is a local concept, tied to each observer's position in space-time. Relativity already tells us that simultaneity is relative. Two events that appear simultaneous to one observer may occur at different times for another. This means there is no single slice of space-time that can be called the present for all observers. The present moment is not an objective cosmic fact. It is a subjective experience emerging from your perspective. This view can be unsettling because it undermines our most immediate experience of time. In daily life, we imagine that the present is constantly advancing, that the future is coming toward us, and that the past is slipping away. But if all events exist equally in space-time, then the passage of time is not an external phenomenon, but an internal one, a product of the way our brains process sequences of events. In this sense, our minds may be projecting a sense of motion onto a timeless landscape. Some physicists and philosophers, however, resist the block universe interpretation. They argue for a growing block model in which the past and present exist, but the future does not yet. In this view, the universe is genuinely evolving, and new moments are being created as time advances. Others support presentism, the idea that only the present is real and that both past and future are abstractions. These perspectives preserve a sense of becoming and change as fundamental aspects of reality, rather than illusions of perception. Experimental physics has yet to provide a definitive answer to which of these models is correct. Relativity itself is consistent with the block universe, but it does not strictly demand it. Quantum mechanics adds further layers of complexity. In standard interpretations, quantum events are described by probabilities that collapse into definite outcomes when measured. This apparent collapse seems to introduce a moment of change, a point at which the future becomes the present. Some interpretations, like the many worlds view, avoid collapse entirely by positing that all possible outcomes occur in parallel branches of the universe. In such interpretations, the sense of time flowing into a single determined future may again be just a feature of our limited perception. What is clear is that the flow of time is deeply tied to the way we, as conscious beings, experience the world. Our brains integrate sensory inputs over short intervals, binding them into a continuous narrative. This process creates a sense of motion from one moment to the next. It also aligns with our ability to remember the past, but not the future, reinforcing the asymmetry of time in our lived experience. But just because we experience time this way does not mean the universe itself shares that experience. Relativity forces us to separate the psychological arrow of time from the physical description of space-time. In the equations, time is simply another coordinate, much like the 3 coordinates of space. You can move along your world line in time just as you move through space, but there is nothing in the mathematics that insists on a universal flow. The perception of flow may emerge from the interaction between our physical world and our cognitive architecture. This distinction between time as experienced and time as described is not merely philosophical, it has practical implications in physics. In cosmology, for instance, the question of whether time began at the Big Bang or whether it extends infinitely into the past depends on how we define time in the first place. In quantum gravity research, where physicists attempt to merge general relativity with quantum mechanics, the very concept of time may need to be reformulated. In some approaches, time is not a fundamental variable at all, but an emergent property of more basic, timeless laws. It is possible that our difficulty in reconciling relativity, quantum mechanics, and the arrow of time stems from treating time as a single unified concept, when it may in fact be layered, part geometry, part thermodynamics, part perception. The flow we feel may belong entirely to the perceptual layer, with no direct analog in the underlying geometry of the universe. This idea challenges the way we think about existence itself. If all moments are equally real, then in some deep sense, nothing is ever truly lost. The past is still there, in its own region of space-time. The future already exists in some form, waiting for us to encounter it along our world line. From this vantage, our lives are not lines drawn across a blank page, but intricate patterns woven into a vast and timeless tapestry. And yet, in the midst of this grand structure, we experience life as a fleeting present. We remember, anticipate, hope, and regret. We measure our days not in the static geometry of space-time, but in the unfolding of moments. Whether or not time truly flows in the external world, it flows for us, and in that flow lies the human story. Perhaps this is the paradox we must live with. Physics tells us that time may be static, a dimension laid out in full. Our minds tell us it is a river carrying us forward. Both may be true, each in its own domain. And as we move through our days, we are both inhabitants of a timeless universe and travelers on a one-way journey, measuring the distance between birth and death in the only way we know, moment by passing moment. Chapter 10. You are a traveler through time. You may never have set foot on a spaceship. You may never have hovered near a black hole or raced close to the speed of light. And yet, you are traveling through time right now, in this very moment. You have been on this journey since the instant you were born, and you will remain on it for as long as you exist. This is not a metaphor. It is a physical fact. Every living being, every inanimate object, every particle in the universe is on a path through space-time, moving from one moment to the next. In the framework of relativity, time is not an external backdrop that flows past us while we stand still. We ourselves are in motion, not just through space, but through time. Even sitting perfectly still in a chair, you are moving forward in the time dimension at a measurable rate. In a simplified sense, if you are at rest in space, nearly all of your motion through space-time is in the time direction. This steady progression is why you can't stop aging, why clocks tick, and why events line up in a sequence you can recall. The idea that we are all travelers through time can be seen most clearly in the concept of a world line, the path an object traces through the four-dimensional continuum of space-time. Your world line begins at your birth and extends into your future, marking every event, every location, every second you occupy. It is unique to you, shaped by your specific movements through space and your experiences of gravity. No two world lines are identical, even for people who seem to share the same life circumstances. Relativity tells us that these world lines are not all traveled at the same rate. Your personal clock, the measure of how much time you experience along your journey, is called your proper time. If you move faster through space, you move more slowly through your own proper time relative to those at rest. If you spend time in a stronger gravitational field, your proper time also slows compared to those in weaker gravity. This is the essence of time dilation, the realization that different travelers can experience different amounts of time between the same two events. In everyday life, these differences are imperceptible. Walking across a room or driving to work will not produce a measurable difference in your proper time compared to someone staying home. The effect is there, but it is far too small to notice without the most sensitive instruments. Still, the fact remains, your journey through time is unique. The second you are living right now is not ticking at exactly the same rate as the second experienced by someone standing on a mountain, flying in an airplane, or orbiting Earth. On Earth, we rarely notice these variations because they are so small. But nature provides us with more dramatic examples. Astronauts aboard the International Space Station orbit at about 7.7 kilometers per second. They experience a tiny amount of velocity-based time dilation, which slows their clocks relative to people on the ground. At the same time, they are farther from Earth's center and feel weaker gravity, which speeds their clocks up relative to the surface. The combination of these two effects results in a net difference of milliseconds over the course of months. Small, but measurable. When astronauts return to Earth, they have aged ever so slightly less than their colleagues who remained here. They have literally taken a different route through time. The differences grow more dramatic at higher speeds and in stronger gravitational fields. If you could travel near the speed of light for a few years of your own proper time, centuries might pass for those you left behind. If you could linger near the event horizon of a supermassive black hole and then return, you would find that the rest of the universe had leapt far ahead of you. These are extreme scenarios, but they are not impossible in principle. They are built into the way space-time works. What's striking is that you don't need to think of these situations as special cases of time travel. They are just different ways of tracing a path through space-time. Whether your world line is almost vertical, as it is when you are at rest relative to Earth, or tilted at a steep angle because you are moving rapidly through space, you are still moving forward through time. The difference is in how much proper time elapses for you compared to others. This perspective reframes the idea of time travel. You do not need a machine to begin the journey. You are already on it. The question is not whether you are moving through time, but how you are moving through time and how your path compares to the paths of others. Even without exotic technology, every one of us is on a slightly different schedule. Two people standing side by side are not perfectly synchronized in the deepest physical sense because they have taken different routes to arrive at this shared moment. Once you see time this way, the familiar concepts of now and later take on new meaning. Now is simply where you are on your world line, and later is further along it. Other people have their own nows, which may not perfectly align with yours. The relativity of simultaneity means that your present is not necessarily someone else's present if they are far away and moving differently. This doesn't change our day-to-day experience. We still make plans, meet at agreed-upon times, and share events. But it tells us that beneath the surface, the structure of time is far richer than it appears. In a sense, our entire understanding of life is bound up in the fact that time moves forward for us. We remember the past because our brains store information about previous events, building a chain of cause and effect. We do not remember the future because we have not yet traveled that part of our world line. This forward-moving experience is what allows us to speak meaningfully about change, growth, and history. Without it, the concept of being a traveler through time would be meaningless because there would be no difference between where you are now and where you will be. Physics leaves open the possibility that the universe as a whole does not experience time's passage in the way we do. The block universe interpretation, which we explored earlier, treats your world line as already existing in its entirety, from birth to death. Your motion through time is then a motion of awareness, not of the universe itself. Whether or not this interpretation is correct, it does not change the fact that your experience of moving along your world line is real to you. The physics gives you the map. Your mind provides the journey. The beauty of this picture is that it places you directly inside the grand architecture of space-time. You are not an observer looking in from the outside. You are a part of the structure, a curve in the fabric, shaped by your motion, your environment, and the gravitational landscape you inhabit. The same laws that govern the orbit of a planet or the fall of a star govern your own progress through time. Every second that passes for you is a manifestation of the geometry of the universe itself. This makes the simple fact of being alive even more extraordinary. From the moment you were born, you have been moving forward in a one-way journey, and every other person, every object, every photon of light has been moving forward along their own. Sometimes your paths run nearly parallel, and you share events closely. Sometimes they diverge, and the same stretch of external time feels different for each traveler. But in every case, you are part of the great procession of all things through the temporal dimension. The relativity of time ensures that there will never be perfect synchrony among all travelers. The universe does not keep a single beat. It is a symphony of many tempos, and you are one of the instruments in that symphony, playing your part according to the conditions of your journey. Whether your seconds are running fast or slow relative to someone else's, they are uniquely yours. They mark your own path from the beginning of your story to wherever it will lead. And this is perhaps the most human way to understand relativity. It tells us that while we are all bound by the same physical laws, we each have our own personal time, our own unfolding of moments. In a purely scientific sense, you are moving through space-time at the speed of light in some combination of space and time. In a personal sense, you are moving through the story of your life, step by step, heartbeat by heartbeat. Physics can measure the differences between your clock and another's to unimaginable precision, but it cannot measure the value of your journey. That part is yours alone. Somewhere in the vast web of space-time, your world line threads its way forward, carrying with it everything you have been, everything you are, and everything you will be. And that, whether you travel far or stay close to home, makes you a traveler through time in the truest possible sense. And that, my friend, is the quiet magic of time, always moving, always carrying you forward on your own unique path. If you're still awake and curious, I'd love to take you on another journey. Just follow me to the next video and we'll keep exploring together. But if your eyes are getting heavy, then let the stars watch over you tonight, and may your dreams be gentle and full of wonder among the endless skies.